Hello, my name is Matthew Inkawhich, and I will be taking you through our work called Tunable Hybrid Proposal Networks for the open world. In this work, we focus on object proposal networks. The goal of a proposal network is to detect and localize all objects of interest in an image. Current state-of-the-art proposal networks are trained with a closed world assumption, meaning that they can only detect objects explicitly labeled in the training data. If they are deployed in an open world environment, one where the model might encounter novel or unknown object classes, otherwise known as out of distribution or OOD, the model can fail in one of two ways. Number one, it can misclassify unknown objects as known classes, or number two, it can just fail to detect the unknown objects altogether. And these kinds of mistakes can yield catastrophic consequences in many applications. For instance, consider a self-driving car that's unable to detect an unexpected moose crossing the road. Importantly, existing work in open world detection fails to consider that the optimal performance of a detector can vary significantly depending on both the data and the application. For instance, a household surveillance system should be more biased towards your known classes, whereas something like a household robot should be more exploratory and able to detect more distant unknown objects. Let's begin by discussing the three existing approaches to object proposal. First, we have learning-free approaches, such as selective search, which rely on handcrafted features. These methods are typically inefficient and not very accurate. Second, we have classification-based learning approaches. An example of such a method is the region proposal network or a class-agnostic faster RCNN. These methods frame object proposal as a discriminative task, and objectness is directly predicted with a classification head. The issue with these models is that they explicitly learn that all non-known or non-ID sampled regions are background, which can often contain out of distribution or unknown objects. So they tend to be very ID biased. A newer style of method is the localization-based learning approach. These models frame object proposal as a localization task, where a localization quality metric, such as centerness or IOU, is used as an indirect proxy for objectness. While these models avoid the explicit ID bias of calling all non-labeled regions background, they remain susceptible to implicit bias depending on the training data. Our solution, which we call the Tunable Hybrid Proposal Network, has three main components. First, we use a hybrid network architecture that allows the user to configure the model's bias tendency for the given data or application. To do this, we use a lambda parameter to linearly interpolate our objectness representation between classification-based objectness and localization-based objectness. Second, we leverage a self-training procedure. Here, we first update the model on the original training data. Next, we generate predictions on the original training images. Finally, we filter and merge the high-confidence predictions into the training data as pseudo-labels. This process can be repeated iteratively. This procedure allows the model to learn from unlabeled objects that exist in most training data. It also requires no auxiliary training data, and we use repeated fine-tuning instead of the more traditional retraining from scratch to make it more efficient. Third, we use dynamic loss components. A localization quality focal loss addresses data imbalance by upweighting the loss contribution from difficult labels and downweighting the loss contribution from easy ones. A weighted box regression loss combats imperfect pseudo-label targets by weighting the loss from each target by its predicted localization quality score, S. When these three components are combined, we get a method that can be readily adapted to different tasks and is capable of leveraging the wealth of unlabeled objects present in most training datasets. To rigorously evaluate our method's open-world performance, we divide the COCO dataset into several disjoint ID-OOD class splits. where the OOD set contains all Cocoa classes that are not in the ID set. We devise class splits that promote an increasing amount of label bias. We start with Cocoa 40, which uses 40 randomly sampled Cocoa classes as the ID set. We then consider where the 20 Pascal VOC classes are ID. We continue by considering a 5-class subset of the VOC classes as ID. And finally, we have a case where the 10 Cocoa animal classes are ID. We measure OOD class recall, ID class recall, and most importantly, all class recall. As baselines, we use a class-agnostic faster RCNN to represent a classification-based learning model, and a object localization net to represent a localization-based learning approach. Note that in all tasks, there exists a THPN model that significantly outperforms the baselines. The best THPN depends on the user's goal and application. If the goal is to maximize OOD recall, the user should set lambda to 0. If the goal is to maintain the highest ID recall, the user should set the lambda parameter to a larger value. Note that for a case like Cocoa 40, where 72% of all instances are ID, it is advantageous to use a larger lambda to achieve better all-class recall. However, in the animal split, if we want to maximize the total recall, or the all recall, it is more important to allow the model the generalization of the localization-based objectness representation, so we would set the lambda parameter lower. We also devise a semi-supervised challenge. Here, we use the VOC class split, but we randomly subsample the number of labeled instances that we assume we have access to for training. Intuitively, in low data settings, like VOC 10%, existing solutions will face significant implicit bias, leading to poor ID and OOD generalization. THPN, on the other hand, can be tuned to easily outperform the baselines on all splits. Interestingly, a THPN with lambda equals 0.1, trained with just 25% of the labeled VOC samples, can outperform a faster RCNN model trained with 100% of VOC samples. To conclude our numerical results, we consider the following 3 figures. In the figure on the left, we visualize the all-class recall of our method compared to the baselines across our devised evaluation splits ranked from least to most biased. Note that unlike OLN, our method maintains very high performance in ID biased tasks such as Cocoa, while unlike faster RCNN, it maintains good total performance in very OOD biased tasks like the animal split. As expected, the optimal lambda decreases as the task bias increases. The 2 tables on the right show that our method significantly outperforms the top learning-free and learning-based baselines on the common Cocoa benchmarks found in the literature. Here, we visualize some pseudo-labels and model predictions from models trained on the VOC5 task. Note that our self-training approach is able to yield high-quality pseudo-labels, which significantly improves the generalization of our method to unknown object classes. The most common failure case that we observe from our method is that it produces some high-confidence predictions on parts of OOD objects rather than localizing the entire OOD object. In conclusion, the wide variety of data bias and desired model behaviors in open-world detection tasks renders any one-size-fits-all proposal solution insufficient. We introduce a powerful new class of proposal model that can be easily adjusted to suit the gamut of challenging open-world scenarios. Our novel evaluation challenges test models in a variety of conditions, ranging from large-scale tasks to problems with severe degrees of data bias. Overall, THPN's superior recall of both ID and OOD objects has the potential to enhance a variety of open-world applications. We thank you for listening and invite you to see paper 623 for more details.